Hi everyone, this is Ashley Bedford, founder of the Runtime Diaries, and I am super excited for this question, day 13 of our hashtag 30 Days of Code Challenge with Educative. We are tackling course schedule. Let's get into this one.
Today, we are tackling course schedule, a foundational graph problem involving cycle detection. This problem transforms how you think about dependency systems, recursion, and graphs. And once you understand this pattern, you'll see it everywhere in built systems, package managers, task schedulers, and database transactions. Let's break it down visually. Here's the setup. You're given a number called num courses, representing courses labeled from 0 to n minus 1. You're also given a list of prerequisite pairs. Each pair is formatted as A, B, which means to take a course A, you must complete course B first. For example, the pair 0, 1 means you must take course 1 before you can take course 0. Course 1 is a prerequisite for course 0. In graph terms, this creates a directed edge from 1 to 0. Your task is simple. Return true if you can finish all courses. Return false if there's any circular dependency that makes it impossible. Let me give you a real-world example to make this concrete. Picture a university degree plan that says CS 102 requires CS 101. CS 201 requires CS 102. CS 101 requires CS 201. Now you're stuck. You can't take CS 102 without CS 101. You can't take CS 101 without CS 201. And you can't take CS 201 without CS 102. There's no valid starting point, and you're trapped in a circular dependency. That's a cycle, and that's exactly what this problem is asking you to detect. The entire problem boils down to one question. Do any courses depend on each other in a loop? If yes, it's impossible to finish all courses. Return false. If no loop exists, you can complete all courses in some valid order. Return true. This is a pure cycle detection problem in a directed graph. That's the core insight. Once you see it as a graph problem, the solution becomes clear. Beginners usually stumble on this problem for a few common reasons. First, they only track whether a node has been visited, but they forget to track whether a node is currently in the recursion path. That distinction is critical for detecting cycles. Second, they start DFS from only one course, assuming that's enough, but the graph might have multiple disconnected components. You need to check every course. Third, they build the graph in the wrong direction. For a prerequisite pair A, B, you need to create an edge from B to A, not A to B. Direction matters. Fourth, they don't understand the difference between visited and visiting. Those two states mean completely different things, and confusing them leads to incorrect cycle detection. The critical idea here is that a node can be in one of three states, and understanding those states is the key to this problem. The naive idea is, let me start from a random course and follow its prerequisites until I reach the end. But this approach falls apart for several reasons. First, the graph might have multiple separate components that don't touch each other. Exploring one component doesn't tell you anything about the others. Second, a cycle may hide in a different branch of the graph. If you only explore one path, you'll miss it. Third, a node may appear in multiple paths. Just because you've visited a node once doesn't mean you've checked all possible cycles involving that node. Fourth, exploring one path isn't enough. We need a systematic, graph-wide strategy that checks every node and every edge. Here's the correct way to think about this problem. Every node in the graph can be in one of three states. State 1 is unvisited, which we can represent as 0 or simply not being in any set. This means the node has never been explored. State 2, visiting, which we can represent as 1 or being in a currently visiting set. This means the node is currently part of the active DFS recursion path. We're in the middle of exploring this node and its descendants. And state 3 is visited, which we can represent as 2 or being in a fully visited set. This means the node has been fully processed. We've explored it and all its descendants, and we know it's safe. No cycles involve this node. A cycle appears exactly when we reach a node that's marked visiting. This means we've looped back into our current recursion path. We're trying to visit a node that we're already in the process of visiting. That's a cycle. Let me show you what this looks like in practice. Imagine DFS is exploring a path through the graph. First, we visit node A. We mark A as visiting, meaning we're currently exploring it. From A, we move to node B. We mark B as visiting. From B, we move to node C. We mark C as visiting. Now from C, we try to move back to node A, but wait, A is already marked visiting. It's still in our current recursion path. We haven't finished exploring A yet. This means we found a cycle. A depends on B depends on C, and C depends on A. That's a loop. We immediately return false. Building the graph correctly is absolutely critical. Get this wrong and your entire solution fails. For each prerequisite pair, A, B, the problem states that B must be completed before A. In other words, B is a prerequisite of A. So the dependency direction is B must come before A. In graph terms, this creates a directed edge from B to A. We're representing B points to A, or B enables A. In code, this looks like graph key of B dot append A. Many beginners reverse this and create an edge from A to B, which completely breaks the logic. Direction is everything in directed graphs. Make sure you're building edges from prerequisite to dependent course. Another naive attempt is to simulate taking courses. The idea is sort courses by their prerequisites, remove courses that have no prerequisites, mark them as completed, and repeat until all courses are removed. But this approach has serious problems. First, it's inefficient. You're repeatedly scanning the entire course list. Second, it doesn't guarantee correct cycle detection. You might miss cycles that are hidden in the dependency structure. Third, it fails on disconnected graphs. If two parts of the graph don't interact, this approach can give incorrect results. And fourth, it's way more work than needed. There are cleaner, more direct ways to detect cycles. Here's the correct DFS solution. It's clean, elegant, and efficient. For each course in the graph, first, we check if the course is already marked visited. If so, skip it. We've already fully explored this node and know it's safe. Second, check if the course is marked visiting. If so, we've found a cycle. This node is in our current recursion path, and we're trying to visit it again. Return false immediately. Third, mark the course as visiting. We're now in the process of exploring it. Fourth, recursively run DFS on all children of this course. In other words, explore all courses that depend on this one. Fifth, after finishing DFS on all children, mark the course as visited. We've fully processed this node and all its descendants. It's safe. If any DFS call returns false, indicating a cycle was found, propagate that false up the call stack. If we finish exploring all courses without finding a cycle, return true. Time complexity is O of V plus E, where V is the number of courses and E is the number of prerequisite pairs. We visit each node once and traverse each edge once. The space complexity is O of V for the recursion stack and state tracking. We can also solve this problem using Kahn's algorithm, which is an iterative approach based on topological sorting. The key concept here is indegree. The indegree of a node is the number of incoming edges, which in this problem means the number of prerequisites for that course. Here's how Kahn's algorithm works. First, compute the indegree for every course. Count how many prerequisites each course has. Second, find all courses with indegree 0. These are courses with no prerequisites. They can be taken immediately. Add them to a queue. Third, process the queue. For each course in the queue, remove it from the graph. This means removing all edges from its course to other courses. For each edge you remove, decrement the indegree of the target course. Fourth, if any course's indegree becomes 0 after decrementing, add it to the queue. It now has no remaining prerequisites. Fifth, keep processing until the queue is empty. Finally, count how many courses you processed. If you processed all of them, there's no cycle. The graph has valid topological ordering, so you return true. If some courses remain unprocessed, they're stuck in a cycle. Return false. The time complexity here is O of V plus E. We process each node and edge once. The space complexity is O of V for the indegree array and queue. Both approaches are optimal and correct. Which should you use? DFS is best when you want explicit cycle detection and prefer recursive reasoning. It directly shows you the cycle in the recursion stack. If you're comfortable with recursion and want to understand the structure of the cycle, DFS is a great choice. Kahn's algorithm is best when you want a topological ordering and prefer iterative queue-based logic. It's easier to implement without recursion, and it naturally gives you a valid ordering of courses if one exists. If you need to actually output the order in which courses should be taken, Kahn's is the way to go. You cannot go wrong with either. They're both O of V plus E, time complexity, and both solve the problem correctly. Let me walk through a concrete example using DFS. Say we have prerequisites from left to right, 1, 0, 2, 1, 3, 2, and 1, 3. This creates the following graph edges. 0 points to 1, 1 points to 2, 2 points to 3, 3 points to 1. Notice that last edge. 3 points back to 1. That creates a cycle. Let's trace the DFS starting from course 0. We mark 0 as visiting and explore its children. 0 has an edge to 1, so we visit 1. Mark 1 as visiting. 1 has an edge to 2, so we visit 2. Mark 2 as visiting. 2 has an edge to 3, so we visit 3. Mark 3 to visiting. 3 has an edge to 1, but 1 is already marked visiting. We're trying to revisit a node in our current path. Cycle is detected here, so we return false. The courses cannot be completed. Let's solve the same example using Kahn's algorithm. Prerequisites from left to right are 1, 0, 2, 1, 3, 2, and 1, 3. First, compute indegrees for each course. Course 0 has indegree 0. No prerequisites. Course 1 has indegree 2. It requires course 0 and course 3. Course 2 has indegree 1. It requires course 1. Course 3 has indegree 1. It requires course 2. Start with all courses that have indegree 0. That's just course 0. Add it to the queue. Process course 0. It has an edge to course 1. Remove that edge, which decrements course 1's indegree from 2 to 1. Now the queue is empty. Course 1 still has indegree 1 because it also requires course 3. No other courses can be added to the queue. We've only processed one course out of 4. The remaining courses are stuck in a cycle. Return false. Let's talk about edge cases you need to handle. If there are no prerequisites, the answer is always true. Every course can be completed immediately. If a course has a self loop like 1, 1, meaning course 1 requires one course, that's an immediate cycle. Return false. If the graph has disconnected components, you must check all of them. You can't just start DFS from one node and assume that's enough. If there's a very long chain of dependencies with no cycles, that's perfectly valid. Return true. If you have a large, directed, acyclic graph or DAG, that's also valid. Return true. These edge cases validate whether your cycle detection logic is correct and complete. Both approaches have the same time and space complexity. The time complexity is O of V plus E, where V is the number of courses and E is the number of prerequisite pairs. We visit each course once and traverse each edge once. The space complexity is O of V. We need storage for the graph structure, plus tracking state for each node. In DFS, this includes the recursion stack. In Kahn's, this includes the indegree array and queue. These complexities are optimal. You cannot solve this problem faster than O of V plus E because you must at least look at every course and every prerequisite pair to know what the dependencies are. Here's what I want you to remember from this problem. First, this is a cycle detection problem in a directed graph. Once you see it that way, the solution becomes clear. Second, the state visiting means the node is in your current recursion stack. It's part of the active path you're exploring. Third, revisiting a visiting node means you've found a cycle. That's the moment you return false. Fourth, build your graph edges from prerequisite to dependent course. For A, B, create an edge from B to A. Fifth, you must explore every component of the graph. Don't assume checking one node is enough. Sixth, both DFS and Kahn's algorithm are correct and optimal. Choose based on your preference for recursion versus iteration. If you learn this pattern, dozens of other graph problems become easier. Topological sorting, dependency resolution, build order determination, and task scheduling all use these exact same techniques.
And that's a wrap for day 13. If you like this video, like it down below, share it with a friend, comment, and we would love to have you. So subscribe to our channel, and we will see you next time.